Okay, so this lesson will pick up where the last one left off with the idea of conditional probability. And the big idea behind conditional probability is if we know an event has or hasn't happened, does that make another event more or less likely to occur? And we use the words dependence and independence to describe these ideas. So we say that events are independent if the outcome of one has no effect on the outcome of the others. In other words, if I know something has happened, then that doesn't make anything else more or less likely to happen. But if the outcomes of an event are contingent on another event, then we say that those are dependent. So knowing that the first event has occurred, does that make something else more or less likely to occur? And this first example kind of models that idea. It says that we are going to make a license plate that consists of 3 letters followed by 3 numbers. And we want to know how many different license plate numbers can we create using that model if no repetitions are allowed. So we have 6 digits. The first 3 digits are letters. I'm going to do an L for letters. And then the last 3 digits are going to be numbers. And it says that no repetitions are allowed. So if we're looking at our first digit, we have 26 different options for letters. But what letters we can select for our second are dependent on what we selected for our first. If we got the letter B right here for the first, then this one could be any letter other than B. So in other words, dependent on what we got for our first letter, now there are 25 options for the second letter. And then in our third letter, because we have no repetitions, we can't repeat any of these 2 digits. So whatever letter we select for our third digit is also dependent on what we've selected for the first 2, which means that we have 24 possibilities for our third digit. Now when we get to the fourth digit can be a number. And since we haven't selected any other numbers, it could be any number from 1 through 9 or 0. So there's 10 possibilities there. Then again, our second number or our 5th digit is dependent on what we selected for our first digit, which means that we can't repeat. So now there are only 9 possibilities for our 5th digit, our second number. And our third number, there are only 8 possibilities because we've already selected 2 for our first. So if we apply the fundamental counting principle, we can find the number of combinations simply by multiplying all of those together. And it turns out that there would be 11,232,000 different digits or different numbers, license plate numbers, we could create using this algorithm with 3 letters, 3 numbers, and no digits that repeat. So we looked at this idea of independence before just a little bit. We said that if 2 events are independent, then the probability that both of those things will occur, both A and B, is simply the product of each of those outcomes. So the probability of A and B, or A intersect B, because we're looking for those overlapping regions, would just simply be the probability that A happens times the probability of B happening. And the reason behind this is knowing that A has happened doesn't change the likeliness or the probability of B happening, and vice versa. And so we call this rule the multiplication rule for independent events. So this next example models independent events. We have a die, and we're going to roll the die twice. So if we're talking about a 6-sided die, the probability of an even number is 0.5, half. And the probability of an odd number is 0.5. We want to know what is the probability of rolling an odd and an even number. So the probability of an odd number and an even number, or the probability of odd intersect even. Each roll of the die is going to be independent. When I roll on the first roll is not going to affect the likeliness of anything on my second roll. So for that reason, the probability is just going to be the probability of rolling an odd times the probability of rolling an even, since each of those rolls are independent of each other. So we would have 0.5 times 0.5 would give us a probability of 0.25 or 25%. However, If the events are dependent, then we have to change this rule a little bit. We can't just use the multiplication rule for independent events, because if event A has already happened, then that changes the likeliness for our next event. It might be more or less likely depending on whether or not A has happened. So in dependent events, the outcome of one event does depend on the outcome of another. So we must find the probability of that event happening given that the first event has already happened. We write the probability of an event B happening given that event A has happened using this notation here. And we just read that as the probability of B given A. So what is the likeliness that B will occur if we already know that A has occurred? And we can calculate the conditional probability using this formula. It turns out that the probability of B happening given that A has happened is the probability of A intersect B, or the probability of A and B happening, divided by the probability of A. And it might be a little bit difficult to see where this formula comes from, but when we actually start to apply it to some numbers, you'll start to see why. So we're going to go back to that example that we looked at in the last lesson, where we surveyed 192 people about their political opinions. The respondents were asked whether they identified as liberal, moderate, or conservative, and then their gender was recorded as well. So for the sake of time, I'm going to go ahead and put in our numbers here because we've already added these up. We know that there were 85 who identified as liberal between both genders, 80 who identified as moderate between both genders, and 27 who identified as conservative, for a total of 192. We also determined that 77 of the respondents were female and that 115 were male, just by adding those values up. So question A wants to know what is the probability that a student that is male is conservative? So we're putting this condition. We're saying that if we know that the student is male, what is the probability that that student will also be conservative? So in the previous notes, we just kind of narrowed it down to those that were conservative and those that were male, and found the probability those that were male rather, and then looked at what percent of those males were identified as conservative. But I want to approach this using that formula for conditional probability that we just looked at. And according to that formula, the probability that a student is conservative, given that we know that the student is male, would be equal to the probability that that student is both conservative and male, divided by the probability that they are male. So if we look at our table, those that identified as both conservative that were male were 21. So 21 out of 192 of our respondents were both conservative and male. We're going to divide that by the probability of being male. Well, in our survey, we had 115 out of 192 of the respondents that were male. And to simplify this, notice that they both have a denominator of 192. So I'm going to multiply the top and the bottom by 192 so that those cancel out. What that leaves me with is 21 out of 115, which would be about 0.183. So about 18.3% of those males would have identified as conservative. If we had gone back to our previous techniques, we would have narrowed it down to just the male, and so our total population would have been 115, divided by, of those groups of males, the numbers who identified as conservative, 21. So we still end up with the same ratio that we would have had if we had just narrowed down our results based on the table. The idea here is that we could have just jumped to this, but I kind of want you guys to see where this formula comes from and why it works, because we won't always be given all of the numbers for all of the possible outcomes. Instead, they might give us probabilities, and we can use these formulas regardless of whether we have the table or the actual probabilities of each possible outcome. So let's go ahead and take a look at another one using this information. Question B wants to know, what is the probability that a student is female given that the student is liberal? So again, we're putting this condition on it. We want to know, what is the probability that a student is female given that we know the student selected liberal? And again, according to our conditional probability formula, that would be the probability that a student is both female and liberal divided by the probability that the student identified as liberal. So if we look back at our table, we had 135, or not 135, just 35 who identified as both liberal and female, so 35 out of 192. And we had a total of 85 out of 192 between both genders who identified as liberal. So again, we multiply both the top and bottom by 192, we end up with 35 over 85. And if we had used our table and only looked at those who identified as liberal, we would have had a total of 85, and 35 of those 85 would have been female. So we end up with a probability of 0.412. So looking at just the liberals, 41.2 of those surveyed were female. We can also use this conditional probability formula to give us a multiplication rule that does not require independence. So we can use the general multiplication rule for independent events and just multiply the probabilities together if we know the outcomes aren't dependent on one another. But if they are, we can alter this formula just a little bit to come up with a probability formula for both events A and B happening. If we take our conditional probability formula and we just simply multiply both sides by the probability of A, then those cancel. So it turns out that the probability of A intersect B, or the probability of A and B, if the events are not independent, is the probability of A times the probability of B given that A has happened. We just call this the general multiplication rule. So it doesn't matter whether or not the events are independent in this rule. And note that this formula would work for independent events, because if the probability of B is not dependent on A happening, then the probability of B given A is just the probability of B. In other words, whether or not A has happened, the probabilities will be the same. This idea also gives us a test for independence. If we want to know if two events are independent of each other, we can look at this idea. If knowing that A has happened has no bearing on the likeliness of B, in other words, if B is just as likely to happen if A has happened as if it hasn't happened, then we know that those two events would be independent of each other. So we can use this idea as kind of a general test to see if two events are in fact independent, or if knowing that A has happened makes B more or less likely to occur. And that's what we're looking at in our next example. In this one, it says that students were surveyed in middle schools around a Texas school district, and students were asked, among other things, whether their primary goal in school was to get good grades, to be popular, or to be good at sports. And the results are summarized on the table below. So again, we broke it down by gender, male and female. Perhaps we suspect that whether or not the student is male or female might affect their result in some way. So if we total up these numbers, we have 117 males that said grades were most important and 130 females. So 247 of the students surveyed said that getting good grades would be their primary goal in school. If we look at those who said being popular, we had 50 males and 91 females. So if we add those together, we have a total of 141 students who said that being popular was their primary goal in school. And then finally, we had our group who selected that being good at sports was their biggest goal. We had of those 60 male and 30 female, so 90 students total responded that they thought that being good at sports was their primary goal in school. We add all of those together, our 247 who said grades, our 141 who said popular, and our 90 who said sports. We get a total of 478 students total that were surveyed. We also want to total up the number of males and females. So if we take the 117 males who said grades, the 150 who responded being popular, and the 60 who responded that sports were most important, we see that we have a total of 227 males that were surveyed. And if we do the same thing with females, we'll take the 130 who selected grades, 91 who selected being popular, and 30 who selected being good at sports. We see that we had 251 female students who were surveyed. And again, if we add our male and female students, we'll get our total number of students, which was 478. So the first thing that we want to know is whether or not wanting to get good grades is independent of gender. In other words, is knowing whether or not the students said they wanted good grades make them more or less likely to be a certain gender? So to determine that, I'm going to compare two probabilities. The first probability I want to know is whether or not any specific gender was more likely to occur given that they said good grades. And we can pick any gender we want, male or female. For this one, I'm just going to go with our male students. So in other words, what is the probability that the student was male given that they selected that good grades were what was most important to them? So if we're looking at only the students who selected good grades, we had 117 males out of 247 students total. So if we're only looking at the students who have good grades, the probability that the student is male if they selected good grades would be approximately 0.47. So about 47% of those students who said that grades were more important were males. Now we want to compare that to just the probability of the student that we selected being male. In other words, were we more or less likely to have male students if we just looked at students who selected good grades versus all of our students overall? So if we look at all of our students, we had 227 male students out of 478 total students that were surveyed, which also gives us approximately 47%. In other words, if we were talking about just the students who selected good grades as their response, they were no more likely to be male or not male than just all of the students that we selected overall, which means that these events are independent of each other. So we'll just kind of write that out. Since knowing whether a student wants good grades makes them no more or less likely to be male, these events, Lacey, are independent of each other. Now in example B, we're wanting to know if being good at sports and gender are independent of each other. And so we're going to do kind of a similar test. And the last example, I went with the male students, and this one I'm just going to go with the female students. But again, you could use any gender for this. So I want to know, is being good at sports independent of Gender. In other words, does knowing that the student wants to be good at sports make them more or less likely to be any one gender? So again, in this example, I'm going to go with my female students. And I want to know what is the probability that a student that we surveyed is female, given that they responded that sports were their priority. So this time I'm looking at only my group who responded that they wanted to be better at sports. And of those who responded that they wanted to be better at sports, we saw that 30 out of the 90 who said sports were female. So approximately 33%. And we're going to compare that just to the probability of being female in general, regardless of what they responded was their priority. And so from that group, we had 251 out of 478 of our respondents that were female, which was approximately 52 or 52.5%. Notice that in this example, these probabilities aren't the same. So even though about 53% of our respondents were female, only 33% of those that had said sports were female, which means that knowing that the student selected sports makes them less likely to be a female student. In other words, female students were less likely to fall in this group than they were in our overall survey, which means that knowing that they selected sports does have some effect on whether or not they were more or less likely to be female. So since students who responded that they wanted to be good at sports were less likely to be female, these events are not independent. Students who responded that they want to be good at sports were less likely to be female these events are not independent. Events are not independent. And again, we could have selected either gender. If we would have selected males here instead of females, what we would have seen is that we already know that 47% of those surveyed were males. We would have gotten a higher percent. We would have gotten that 67% of those who said sports were males. So we would have seen the opposite if we had selected males. In other words, knowing that they were good at sports made them more likely to be male and less likely to be female. Okay, let's go ahead and move on to our next example. And in this one, they just asked us the question, can events that are disjoint also be independent? And this is kind of an interesting idea, the idea of disjoint versus independent, because a lot of times people get those two things confused with each other, and they're not the same. So if an event is disjoint, can it be independent? Or if you know events are independent, can they be disjoint? So I'm going to start by just creating two events that have a probability not equal to 0. So suppose that events A and B, two separate events, have probabilities not equal to 0. In other words, event A has a possibility and event B has a possibility. If you think of event A as the probability of getting an A on your next test, not impossible, so its probability wouldn't be 0. And think of event B as the probability of getting a B on the next test, so also not 0. And because you would either have to be one or the other, let's say that those events are disjoint. So you either get an A on the test or you get a B on the test, but you wouldn't get both. That would be a good example of two events that are disjoint. So since disjoint events have no outcome in common, then the intersection is going to have nothing in it. In other words, since events that are disjoint have no outcomes in common, then the probability of something landing in the intersection of A and B would have to be 0. They have no outcomes in common, so the probability of landing in both is 0. The probability that you'll get an A and a B on your next test is 0. But this creates a problem if we look at our formula for independence. So, but if this is true, then the probability, not B, the probability that B happens given that A has happened would be the probability of A and B divided by the probability of A, which would be 0 divided by the probability of A, regardless of the outcome has to be in one or the other. If it is in A and A has happened, then it can't be in B. The probability therefore. But in order for it to be independent, then the probability of B given A would have to be equal to the probability of B. But if those events are also disjoint, the probability of B given A would be equal to 0. And if they're independent, that would be the probability of B. But this would be a contradiction, because we specifically said that B has outcomes. A contradiction. Since outcome B is not impossible, it does have a probability of happening. Thus, two events cannot be both disjoint and independent. You could be one or the other, but you couldn't be both. The idea here is that if two events are disjoint, knowing that one has happened definitely affects the possibility of the other happening. So for example, if A and B are disjoint and we know that A has happened, they can't both happen. So we know that the probability of B is 0. And on the flip side of that, if two events are disjoint and we know that A has not happened, because they have no overlapping region, then that actually means that the probability of event B has now increased. And since knowing whether or not A has happened means that B is less likely to happen, not going to happen, or more likely to happen if the events are disjoint, by definition, they cannot also be independent. So the idea here is that you could be independent or disjoint, but again, you can't have both of those outcomes in common. So I want to end with the example that we looked at previously about drunk drivers. It says that suppose 78% of drunk drivers stopped are given a breath test, 36% are given a blood test, and 22% are given both. We want to determine two things. The first thing that we want to determine is whether or not a DUI suspect, giving a DUI suspect a blood test and breath test are mutually exclusive or disjoint. We also want to know whether or not the two tests could be independent of each other. So I'd like for you guys to take about 5 or 10 minutes to see if you can answer those questions, and then we'll look at the answer to that in part 2.